Okay, welcome to the third and final screencast for power and electric potential in basic DC circuits. This goes with guide sheet number 4, which is what I'm looking at right here. First is a quick matching using the units. Now, units are a very helpful tool. The more you understand about the units, the easier it is to keep track of everything. The coulomb is the fundamental unit of charge. So the coulomb is a key fundamental by itself, doesn't require anything else. An ampere is defined as 1 coulomb of charge passing an area every second of time. So we say it's the rate of motion of charge, so therefore it's the electric current. That's how we measure electric current. 1 volt is 1 joule of energy for every 1 coulomb of charge. So it's a way to measure how much energy is transferred as you move to different points in an electric circuit and the potential changes. Now, ohms are how we measure the resistance, and the big thing about ohms is to recognize that its symbol is a capital omega. And the reason it's an omega as opposed to an O is that an O looks too much like a 0. It would throw us off. Joules are our unit of energy, so it tells us how much energy is being changed, transferred from one place to another, increased, decreased, as we move around an electric circuit. And then the watt is defined as the 1 watt is 1 joule of energy for every 1 second of time. So it tells us the amount of energy per time, so it's the rate of change of energy, therefore it's the power. If we want to calculate that power, you can actually use the units to figure out, oh, how should I calculate power? Well, for power I need watts. That means I need 1 joule per 1 second. So if I take the volt, which is 1 joule for every coulomb of charge, and I multiply that by current, which is 1 coulomb of charge for every 1 second, the C's cancel out and I'm left with 1 joule for every 1 second of time. So in other words, if you're trying to figure out the power, it's the change in potential difference, times the current flowing. And again, the symbol for current is I, because C is already used for the coulomb. Okay, so the unit of charge is the coulomb, so that's letter A over there. And the symbol for charge would be Q. Could be large Q, small q, it's some kind of Q. The unit of electric potential is the volt, that's C. Alright, so the potential at any point is symbolized by a V. The potential difference would then be symbolized by delta V, the change of potential. The unit of the power is the watt, that's F. And again, the symbol for power is simply P, big P for power. The unit of potential energy, the unit of any energy is the joule, that's E. And energy is also going to be an E. Most often we think in terms of change of energy, so usually it's delta E that we're most interested in. The unit of current is the ampere, so that's letter B. And the symbol for an ampere is an A. It's usually written as a capital A. Now that's the symbol for the unit. Again, the symbol for current is I. So that can get pretty confusing. We have current I measured in amperes A. And then finally, the unit of resistance is the ohm, so that's letter D. And again, the symbol for that is the Greek letter capital omega to keep us from thinking it's a 0. Okay, so we've got one last little circuit here to look at. We've got the potential diagram to draw on the right. So this kind of puts together all the things we've looked at in the other 2 videos and this one so far. And again, you always want to approach it from where is the negative side of the power supply. That's where our potential will be the highest. So we have the biggest V at this point. Our potential will stay essentially the same as we move through wires, but will decrease whenever we go across some item like a light bulb or a motor or a heating element. As we use the energy and transfer it outside the circuit, we will lose potential. That's often called a voltage drop. It's a difference in potential. So C will actually be less than D. And then as we go through the ammeter we're assuming is perfect, so it will not take anything from our circuit. And we get back to A, we will have a potential of 0. Now that means that we're connected by a wire from A to C, so the potential here is also essentially 0. So if we draw that in the diagram to the right, as we start at point B, we have 12 volts. We're okay until we move to point D, we're still at 12 volts. Now there's only one object that actually is going to use the energy in the circuit. So as we go from D to C, we must use up everything that we put in. So point C down here would be at 0 volts, and then point A would also be at 0 volts. No potential left. Okay, so A, clearly from the diagram there on the right, is less than the voltage at B, the potential at B. C is also less than the potential at D. We have dropped our potential. We've lost potential as we've gone through the light bulb. And then B is going to be equal to letter D. We're not going to have any change between those 2 points because we're assuming the wire is essentially perfect. Okay, now in terms of add or remove, again, power supplies will add energy, so they will give us an increase of our potential. So we usually think of them as a positive potential difference. On the other side, in the light bulb, that will be taking energy outside of the circuit. And you can see that the light is leaving the circuit when you turn it on. So we usually think of that as a decrease in potential. So we often call it a drop of potential. And when we are comparing those, we usually think of that as a negative potential difference. Now again, every time you go around any loop in an electric circuit, all of the positive potential increases must be equal to all of the negative potential decreases. So if we have 12 volts of potential added between points A and B, we must have 12 volts of potential lost between points D and C. Now that we know the potential difference there and we know the current, we can calculate the power. As I showed above, it's just going to be the potential difference times the current that flows. There's only one path, so the current everywhere is 2 amps. And we said the potential difference across this light bulb must be equal to the power supply, so that's 12 volts. So 12 volts times 2 amps is 24 watts, capital W. Now, that means this particular light bulb is going to be using 24 joules of energy for every 1 second that you have it turned on. If you want to know the energy over a course of a minute, just multiply that by the number of seconds in the minute. If you want to know by how much it's using over an hour, then multiply it by 3,600. There's 3,600 seconds in an hour. So power is equal to the rate of change of energy, so it's delta E over T, and therefore the delta E would simply be power times time if you solve that for delta E, change in energy. Okay, so that wraps up energy and power in circuits. We'll be moving on to series and parallel combinations next to look at how we can connect multiple objects together in a circuit.